Hi everyone, we're back to talk about lecture 21, which is getting into numerical methods. So up until now, we've looked at exact techniques for solving initial value problems, whether they be continuous or discrete time. With the example here in continuous, because that's what we're going to look at. But there's no general method to find an exact solution to this problem. So we'll use numerical methods a lot of the time. So we're going to go through several numerical methods, and then we'll talk about pros and cons of methods for given problems. So these methods only give us approximations on a discrete set of inputs, right? Even though we are looking for a continuous function to approximate, we really just get discrete points. So the initial condition is exact, but subsequent outputs are all approximate values. In the numerical methods that we're going to look at now and next time, we are only going to look at those that have what we call a fixed step size. So we assume the difference between time k plus 1 and time k. So the steps in these discrete time approximations, those steps are always equal. This condition can be relaxed. So if you're familiar with using OD45, like the MATLAB numerical solver, for example, that uses an adaptive step size. So if it thinks the dynamics are changing faster, it'll use smaller steps, and if they're changing slower, it'll use bigger steps. We're not going to consider that today. We're just going to look at fixed step size first, which is just the basic idea of how to solve these problems. So let's see where we're going to go. If I have this system of differential equations, this can be vectorial, right? That's fine. If I apply the fundamental theorem of calculus, right, and I want to integrate from tk to tk plus 1, then on the right-hand side should be the antiderivative of the integrand, which if this is y prime, is just y at the upper limit and minus at the lower limit of integration. So y tk plus 1 minus y at tk. When I plug this formula into equation 2, or sorry, I plug equation 2 into this formula, I don't have a y prime anymore, which I don't really know, but I have instead the integral of function f, which I am given. And if I solve for y at tk plus 1, I get a formula that looks like this, right? So everything on the right-hand side is in terms of tk up until tk plus 1, and it gives me this updated value for my function y. So the idea is that we're going to use different numerical methods, or how numerical methods differ is in how to approximate this integral here. So why can't I solve this exactly? There's a lot of different ways to approximate an integral, right? So if I use what we'll call like a left-hand rule, saying that if I want to approximate the value of this integral with a rectangle, right? So I have a function, and I say I'm going to approximate the functional value here with the rectangle, the height of the rectangle on the left here. So this is, I guess, the functional value here, the approximation. Then y at tk plus 1 is approximately y of tk plus the area of this rectangle, right? The height at the left-hand side here times the width of the base, which we know is just our h, right? So this would be the most kind of basic way of approximating this integral here. And if I do that, we get a method that we call the forward Euler's method. So in the box here, you can see forward Euler's. So if I want to approximate the solution to this initial value problem at these certain discrete time points, t0, t1 up to tn, with the step size of h, I set my initial condition, and I just say that y at k plus 1 is y at k, the kth step, plus this area of the rectangle, right? So the functional value at time k and at yk times h, the the width of the base of the rectangle. And so with that, I have an exact value for y0 and approximate values for y1 all the way up until yn. Let's see how we can implement something like this for a problem that looks familiar from a couple lectures ago. So we have this SIRS model for disease transmission. I have two states, number susceptible and then the number of infected individuals. And I have these two initial conditions. So let's call y this vector of s and I, which changes for time t. And we can choose a step size, say it's 0.1. And let's do an Euler's approximation to see if we can find y1, which would be, if I'm starting at t is equal to 0, this would be s and I at time 0.1 for whatever the units of time we use are. So we know from the Euler's formula that y1 y0 plus h times f at time t0 and y0, right? So y0 is my initial condition for s, so 3/2, and for I, so 1/2, plus h, which we've set at 0.1, times f of 0, and what's y0? 3/2, 1/2, right? Great. So then what's the functional value? These guys stay the same. So f, when I plug in 0, I look at these equations. There's no t up here, right? But there is, let's see. How do we compute? So if I do this one, 3/2 times 1/2 is 1/4 minus 1/2. 3/4 minus 1/2. Great. And then for the first equation, minus 3/4 plus, so 2 minus s minus I. Well, if I sum s and I, this equals 2, so this whole term is going to be 0. Okay, so this is whatever it is, some number. Oops, sorry, this should be an equal sign. Here we go. This is some 3/2 minus, I'll write this 0.075, I guess. 0.75 divided by 10, and then this is going to be 1/2 plus 0.025. Okay, do this in MATLAB on another screen, so this should be something like 1.425 and 0.525. And so the question was, this, by the way, is y1, which is an approximation for y at time 0.1, right? So then an approximation for the number of infected individuals at time 0.1 is going to be the second term here. So it's going to be this number in millions, so 525,000. Awesome. Okay. So what's the big idea? The big idea is that numerical methods for systems of first order equations can be used to approximate solutions for second order or higher scalar equations, right? Because this was a system of 2 first order equations, which could also be written as a second order system, right? So we can look at systems of any order with this type of trick, because we're only looking at, say, one time step back. So we only really need the fundamental theorem of calculus to relate y and y prime through the function f. So let's look at another example where we can see this more starkly. So we have a second order scalar initial value problem. I want to write it as a first order system. And then with the step size of 0.1, I want to do forward Eulers to find y naught, y1. Yeah, great. And then relate this back to x, what we're looking at here. So as we know, done this a bunch of times, I'm going to say that y1 is x and y2 is x prime. And so that means that y, the vectorial differential equation, y prime is going to be y2, so y1 prime is y2, y2 prime is all this junk moved to the right hand side except for x double prime. So 2 minus t squared y1 minus y2. Hopefully that's clear. So I can write this as a matrix. 0, 1, minus t squared minus 1 times y plus 0, 2. And the initial condition here should be 1 for the first element and 0 for the second element of y. Great. So we want to use the same formula that we just used to compute y1. Well, we know why not. Exactly. y1 is just going to be y naught plus h times f at t naught and y naught. Excellent. So this is 1, 0 plus, we said our h was what? Oh, 0.1. And then f is going to be this function upstairs, right? F is 0, 1, t naught is 0, minus 1, y naught is 1, 0, plus 0, 2. Hopefully that's good. So this is going to be 0. Of course, you could do this all in MATLAB. 0.1 times. This first element is 0 plus 0. Second element is also 0 plus 2. So I get 1 and then 0.2 as my solution. So the question is, what is an approximation for x of t? Remember, the first element was y1, which is x. The second element was y2, which was x prime. So this means that if I want to look for just x, it's going to be the first element. An approximation for the value of x at time is 0.1 is 1. Okay. Hopefully that's good. So that is the most straightforward kind of method that we could use to look at an approximation for the integral, of f. But there are better approximations, right? You probably remember this from your calculus class. So instead of just choosing the right or the left-hand side of the rectangles, say to approximate the area under a curve, we can also do the trapezoid rule. You approximate the area under a curve with trapezoids. And so if you recall, the trapezoid rule to approximate an interval like this looks something like this. So h, we're doing a fixed step size, right? And then I'm going to take the average of these, the functional value at the left-hand side and the functional value at the right-hand side. And yeah, divide by 2. So I plug that into my equation 5, right, which is just my discrete time update, that y at tk plus 1 is approximately y at tk, and then times h, plus h times this approximation for the area under the curve. So if I use this, this is of course like an approximation here, but if I say that yk plus 1 is a good approximation for this guy, move on to page 5. We say, oops, here we go, that y at 10k is really just yk of our sequence that we're approximating. And we can put that into all these functions in our approximation here. So what you'll notice is that k plus 1 is going to appear on both sides, right? Or y at tk plus 1. So what are we going to do about that? So how do we get rid of this? Because this is also inside the function. It's not like I can even kind of solve for it. I don't know, this function's invertible. Like, it's pretty hairy. It's implicit. But I remember I can use the basic like Euler's method to approximate this guy, right? So I'm going to use Euler's method approximation that y at 10k plus 1 is y at k plus h times f at tk and yk to approximate this guy in here. We get another method, which we call, well, I call it Hune's method. I guess I should have looked it up and listened to it before, but I've always said Hune's. But this is the approximation that we get. So it looks a lot like Euler's, right? This looks like the trapezoid rule. And now where the trapezoid rule would have been f tk yk plus f tk plus 1 yk plus 1 over 2. Now yk plus 1 is approximated with this Euler's method. So in the box on page 5, you can see Hune's method all written down. So I again want to approximate the solution to this same initial value problem. I set my ICs, and now I use a slightly different formula, very much similar to the Euler's, right? And I get these discrete time approximations. So we did an approximation to a scalar first order system using Euler's. Let's consider the same system here. And let's do an approximation here with Hune's with a different h. It's okay. Here we go. And I'll be starting on the next page in your notes here. There we go. Start up here. Okay. So my y naught is all going to be the same, right? This guy's going to be 1, 0. And let's solve for the different things that we're going to need for Hune's method, right? We know that we need f at 0, or so f at t0, which is 0, and at the initial condition. We're going to need that. So what is that? That's going to be 0, 1, 0, negative 1 times 1, 0 plus 0, 2. So we had found this guy before. This is 0, 2. We are also going to need y naught plus h f at 0, 1, we just found, sorry, 1, 0. So that's what we're going to need for, if I kind of push this down here, for this part here. So we have this, now we're going to have this. So we know this is this, so 1, 0 plus, we said h was, what was h? 1/2. And f at 0, 1, we already found to be this guy here. So we get 1, 1. And the last thing that we're going to need is f at tk plus 1, which is 1/2, comma, yk plus h, f of tk, yk. So this guy we found right here. So we have 1, 1 plus, oh, sorry, not that. This is when we plug into the function, right? So 0, 1. Now this term isn't 0, it's minus t squared. So minus 1/4 minus 1. Now times 1, 1 plus 0, 2. Is that right? Okay, that looks okay to me. So what do we get? So the first element here is going to be 1 plus 0, so 1. And the second element is minus 1/4, so minus 5/4, plus 2, which is 8/4, so 3/4, right? Great. So let's put it all together. So y1 is going to be y0 plus h 0. So h is going to be 0.5. We'll write it like this. We won't combine the 1/2 and the 2 just yet. Plus, times 0, 2 plus this guy, 1 3/4. Oops, excuse me. There we go. So hopefully you can see all that. Okay, so that's 1 0 plus 1/4 times 1, and that's 8/4 plus 3/4, so 11/4. So if I divide by 4, this is 1 plus 1/4, so 5/4, and 11 over 16. So it is what it is, whatever that number is. Okay, so hopefully that implementation is pretty clear. Very algorithmic, but gives you slightly different numbers. And we're going to talk about proving accuracy later, but this approximation is going to be more accurate than forward Eulers. And I think if you remember your calculus class, the trapezoid rule was more accurate than just making the area of the curve a rectangle or a couple rectangles that are either the left or the right hand side of the function. It's easy to imagine that Hume's method is going to be more accurate than forward Eulers. But we have another method to talk about, which will give an even more accurate estimate for that interval. So you might remember Simpson's rule, which gives an even better approximation to the area under a curve for an interval. So when we apply Simpson's to approximate that interval, we get what is called the fourth order Runge-Kutta method. So same initial value problem that I want to approximate the solution to, same ICs, but now when I have this h times f at tk comma yk, or whatever, you know, let's say that interval before I even write that like that. I don't know if you remember, there's a formula for Simpson's rule. It does like say an even higher kind of averaging to approximate the area under that interval, the value of that interval, the area under that curve. If I apply that, I get this method here, and that's even more accurate. So instead of doing this by hand, which I think is kind of useless, I'm going to ask you to do this in MATLAB later, and we're just going to look at results of doing this in MATLAB. I mean, it's not useless to do it by hand, but I think, you know, it's believable if you remember your calculus class, and doing it by hand is not as valuable as seeing the results when you can do it in MATLAB, right, for more than just one step. Because if the other two implementations are clear, I think this is too. So let's consider this second order differential equation here with an initial condition, and this guy This is like our harmonic oscillator we talked about, some forcing. So I have a solution that looks like this. This is an exact solution and you can check. And so we know this is kind of unrelated to how we solve this problem, but just to mention it, this is, so remember we talked about the mass spring system, right? This undamped system that could have potentially like what we call a resonance. So this is forced at the natural frequency, which is the square root of whatever was on the x term in this x double prime plus omega x. This is actually like omega squared. So we expect a term that's going to blow up as time goes forward. And we will see that here. That would demonstrate the resonance in this system. But this is just a toy problem that we want to look at these different numerical integration methods with. So first, let's look at forward Eulers. If I have a step size of 0.1 and I choose to go n is equal to 100 steps. I guess I didn't say this. Number of steps. So multiplying those, that's going to put us at time 10 for whatever unit we have here. So the solid line is the exact solution, and the dots are what we get from the forward Eulers approximation. And you can see as time goes forward, this approximation really starts to break down, not doing so great. If I decrease the step size, I can get something that is more accurate, but much more computation, right? So now I'm doing a step size that's 1/2 as big, so I'm doing twice as many steps to get up to 10, and it's still not great. If I decide to do 4 times as many steps, 4 times as many computations, and a step size of 1/4, it's a lot better, but I still miss stuff. And you can imagine as you go for larger times, this again is going to start to break down. So yeah, the text here says even with a very small step size, the error is visible. So the reason is, and we'll talk more about accuracy later, but forward Eulers is what we call first order accurate. And the Hume's model is second order accurate. So let's take a look at the same result with Hume. So now we're going to go back to the forward, or to the parameters of a step size of 0.1 and n as being 100. Just to recall, that's the Eulers that looked like this, right? Real bad. When I do the Hume's methods of same number of operations, I get this, which is pretty decent, right? So not that many steps and way better than Eulers. But if I try to start to decrease the number of steps, the error comes back. So that was 100 steps. Here it is with only 50. And I start to get lost again, right? Not perfect, not terrible, but not perfect. What's impressive is if I compare this to the Runge-Kutta method. So with a fourth order Runge-Kutta, and I use these same parameters here, so 50 steps, the step size of 0.2, I look at the Runge-Kutta, I am like right on, right? Not visible at all, any error in the system. And if I decrease the number of steps and increase the step size by 2, Runge-Kutta still holds. I don't know if you can see in the PDF of your notes, you'll see these in color, right? So the dots will be red. But now I'm only doing 25 steps, and it's super, super accurate. So fourth order Runge-Kutta is a really nice numerical approximation if you're going to do something with a fixed step size. This is one that is definitely widely used. So my challenge for you is this. It's not hard to code these. So you could try and use MATLAB to implement forward Eulers, Hume's, and fourth order Runge-Kutta and replicate these 7 plots from this lecture. I'll share my code for those with you on Thursday, but let's see if you can do it by then, because I think you can watch a video of me talking through my code, but it's probably more illustrative to try and do it yourself and struggle for a bit. So with Thursday's lecture, I'll post the solution, or a solution, my solution, to how you can code all these 3 algorithms in MATLAB and how I made these plots. All right, that's it. Bye-bye.